Hello everyone, and welcome to today's webinar on Introduction to Partial Discharge on Transformer and GIS. My name is Sanjay Yadav and I will be hosting this session today. Speaker for today's session is Mr. Mohammad Tariq, who is a Technical Director at Megger Middle East Asia. So before handing the mic to Mr. Mohammad, I would like to highlight a few points. You all are muted to avoid any disturbance during the presentation. Do park any question you may have for the Q&A session at the end or share it in chat window. All the questions will be answered at the end of the session by Mr. Mohammad. I now hand over the control to Mr. Mohammad. Mr. Mohammad, over to you, sir.
Good morning, everybody, and thank you for attending Megger webinar on partial discharge testing. And today I'm going to talk about partial discharge testing on power transformers and GIS. The purpose of this is introduction to partial discharge. So I'm talking about basics, and then I talk about partial discharge on GIS and power transformer. This webinar is good for anybody who wants to learn and to be introduced to partial discharge, and then partial discharge testing on power transformers and GIS. At the end of the presentation, I'll take questions, and stay tuned. We will introduce more advanced webinars made by our factory on each specific advanced subjects on partial discharge. However, here we will have a webinar as introduction basis. So basically, talking quickly about insulation and dielectric, there are various type of insulation: thermal insulation, electrical, and sound insulation. When it comes to electrical insulation, keep in mind that there is a difference between electric conductor and insulator, where in metals they have loose electrons, while in organic molecules they have shared electrons. So that plays a role in partial discharge testing, because in a partial discharge to occur, a loose electron is required, called a starter electron. So in metal, it's very easy to have a loose electron, but in organic molecules, since electrons are shared, they need high energy for first electron to be started. So electrical insulator can be polarized by applying electric field. So that's, we call them dielectric. So basically, they have energy storing capacity, insulators, because they are confined within two conductors, which act as capacitor. And they have absorption properties and polarization as well. Moving on, type of insulation used in high voltage insulating materials. There is gases, various gases like air, SF6, liquids, for example, there are mineral oil and silicone oil, various oils, and then there are solids like mica, resin, ceramic. Each one play a role in a different way in partial discharge testing. For example, SF6 gas used in GIS, for example, they show a very fast rise time, and that's why very high frequency, like ultra high frequency UHF, will be useful there due to the very fast rise time of the electron pulses, PD pulses. Okay. Basically, aging mechanisms of these insulations, they always become under thermal stress, under mechanical stress, and additionally under electrical stress. So all of these insulations, they always under electrical stress. Depends on the objects. It can be more or it can be less. They also under thermal stress and mechanical stress. Basically, NFPA states that the insulation breakdown is #1 cause of the electrical failure. So in a medium or high voltage equipment, partial discharge is the first indication of insulation breakdown. So it's a common phenomenon in a solid insulation, like electrical treeing. So being able to detect such failures in early stage will help a lot in avoiding catastrophic failures and correcting the issue at the infancy. What facilities affected? Basically, industrial facilities, commercial, institutional, government, and any utility, they are very affected with that. So let us define what is PD. Basically, IEC 6270 standard, it's a horizontal standards, defines the method of partial discharge testing for all high voltage objects. It states that PD is a localized electrical discharge that only partially bridges the insulation between conductors and which can or cannot occur in adjacent to a conductor. Basically, PD presents when there is a high voltage stress across the void exceeds the dielectric strength of the insulating material. Due to PD, physical and chemical changes may happen. So due to this physical and chemical changes as a result of PD, it will produce emission that we can detect. Basically, PD manifests itself in multiple methods. It can be as a void discharge, is like a void for example, in a solid insulation, it can be like a void, or it can be a surface discharge within laminated areas between two different types of insulation. It can be a corona discharge, for example, due to the sharp edges. Sharp edges, for example, due to the uneven surfaces, whether not a good finish at factory or probably a later stage. It either can happen at factory or in later stage. There are many others like floating potentials as well. So basically, PD will occur due to localized stress. We expect that electric field distributed equally and homogeneously within insulated material. However, due to the imperfection, like we mentioned here, it will cause high electric field, localized electric field, which can cause a localized discharge within the void or within the local field. Now the question come to picture is that how to detect that localized discharge and how that happens. That we'll discuss in next few slides. So basically, a partial discharge phenomena is one of the root cause for the insulation degradation. So every big problem starts as a small issue. So early partial discharge detection prevents a full breakdown and costly damages. Partial discharge analysis also helps to improve the design of the insulation system. That is because by doing partial discharge tests, it helps to improve the design, which can reduce the PD and can increase the reliability of the insulation system. Partial discharge location helps to find failure positions within various available techniques, which we'll discuss some of them in this presentation. It will also help to find location of the PD. And also keep in mind that partial discharge measurement are non-intrusive and can be done online as well as offline with conventional method and unconventional method. We will explain what do we mean by conventional and unconventional method. We briefly also discuss how do we compare online versus offline method. Of course, when it comes to offline method, also there is several type of testing. There are field tests and factory tests and lab tests. So all of these make small differences, and all of these are offline. Okay, so how PD occurs? Basically, for occurrence of partial discharge, two conditions must be met for PD to happen. First, the local electric field must have reached their critical inception field. That means for a PD to happen, electric field should be higher than a specific value. Once that exceeded, that will cause one factor to cause a PD. Another important thing it needs to be considered is that a free electron must be available to start the discharge avalanche. What we mean is that a free electron will be accelerated because of the high electric field, and once free electron accelerates, it creates high energy collision, and it also free other electrons within that insulation surrounding. Then after that, an avalanche will happen, electron avalanche, and that electron avalanche will cause a pulse at that location. Two main processes to derive this initial electron. First is that depends on the location of the PD. If there is a free electron available, then it can happen very fast. But if in a typical insulation, for example, for a surface laminated area where semiconductor area, the free electron might be available in metallic surfaces. However, in a middle of solid insulation, for example, usually the material having covalent bond, so a free electron is not available. So how that happens? PD happens then. In that case, statistical properties of cosmic rays states that up to every 15 minutes or 1000 seconds, there is cosmic photon hit, and that will cause free electron availability, which makes that available. So that's why in some insulation types, the minimum test of 15 minutes is required to initialize the PD for location where a free electron is not available, like a solid insulation. Okay, so a quick note regarding online versus offline testing. IEC 6270 defines mostly related to offline testing. It is very important for laboratory and workshop setups, and it requires separate power supply to induce PD activity. That means you need a power supply which generates a high voltage output to the object. And there are various high voltage sources, depends on the object under test. It can be either resonance system, or it can be damped system, AC system, AC hypot, very low frequency like for cables, or compensated transformers. So various power supply sources can be used. Keep in mind that for offline test, device under test has to be taken out of service. This is one disadvantage for offline testing. A gas type pressure and humidity may differ from operating conditions, so this has to be logged as well. That means what gas type or insulation type, or the pressure at which gas is, humidity at which being measured as well. In offline test, a noise is less. the benefit. Now let's consider quickly some of the benefits of offline testing. The offline testing, for example, noise can be handled and mostly reduced or eliminated. Because since there is offline test, there is no high voltage surrounding noise. Other noises can be reduced significantly, like noises coming from power supply unit using filters, for example, and then other noise sources using gating can be eliminated. The benefit of offline testing, there are a couple of benefits. First, a calibration is possible, which means that based on IEC 60270, a calibrator box, small box, applies a non-value of pulse through the object, and that can be measured and calibrated for the setup. So measurement is much more accurate during offline test to give a accurate indication as well. The noise is much less compared to online testing. Another important thing is ability to measure the partial discharge inception voltage and partial discharge extinction voltage, which means we can measure PD at which voltage happens. So that means you can control the output voltage from the high voltage source, increase the voltage gradually, and find out at which voltage you get the PD. And then reduce again, that means at which voltage PD will be eliminated. That's very important. For example, let's say you have a measuring a transformer, and in that case you can find out, increase the voltage gradually and find out which voltage PD happens. If that voltage below U naught, which means that the transformer will always exhibit PD. But if it is above U naught, that means the PD won't happen initially but will be ignited. Depends on the level of voltage, then we can find out if that can ignite it during inrush start of the transformer, inrush current. With the extinction voltage also, we can find out if that can be eliminated quickly or will sustain. So all of these factors are benefit of offline testing. Basically, offline tests give more accurate and more control over measurement of partial discharge testing due to the lower noise and calibration and control of high voltage source. However, not to forget the benefit of online testing. The online testing, one of the biggest benefit is that you can measure PD while the equipment is online. So that means you can measure more frequent. Offline, you cannot do that every year, for example, or frequent, you can do that every several years. But for online, you can do that even every 6 months or every year. Since you can, at any given time, you can go and connect your equipment. Depends on the type of measurement discussed later, whether you have sensors installed or not. Sometimes you can install sensors while online. I'll discuss that more details later. So trending ability also is one of the big factors in online. That means you can trend the result for the partial discharge, whether it's increasing or keeping the same level. And then you can also keep into consideration the power loading, temperature and humidity changes, how that changes the PD. For example, whether transformer at higher load will exhibit more PD or not. For example, that can be realized during online test. Okay. Let us discuss, we mentioned when it comes to PD measurement, there are two methods for PD measurement: conventional method and unconventional method. In a conventional method, it means that you connect the sensors directly to the output or to your object, and basically you need to realize that localized PD, you cannot measure it directly in the middle of the insulation, but you can measure the result of it, which means that PD will propagate, the pulse, a high frequency pulse happens in the middle of insulation. It propagates through the network. You know that the insulation combined like a transformer and GIS is a complex impedance network. So the pulse will travel through that network, and then it will arrive eventually at the terminals at which you are measuring. To be able to decouple and get those high frequency pulses, you need a coupling capacitor, here represented as CK. So CA is your object being measured, and CK is your coupling capacitor. Always in conventional direct measurement method, a coupling capacitor is needed along with a measuring impedance to decouple and measure the value of the PD pulses. So we call it measuring impedance. Combination of this, you will be able to measure the level of the pulse in picocoulomb. Picocoulomb, you know, that is the integration of current pulse in time. So that means it gives you a level of the apparent charge. Keep in mind that this apparent charge is not direct measurement of the pulse itself. It's an apparent charge, which means that the value you measured at the measured terminals after original pulse propagates through the insulation. So it depends on the medium at which it travels. The frequency will be dispersed and reflected. So the pulse will have a lower frequency compared to what happens at original location. However, still you will be able to measure the apparent pulse at the measuring terminals. So this is called a conventional method. Okay, so keep in mind that a coupling device or a coupling capacitor designed to achieve optimum sensitivity. So it forms a principle of four-terminal network referred to as quadrupole. That's why we call it quadrupole, which measures the pulse value, apparent pulse value, which connected typically in series with the coupling capacitor. Our coupling capacitors always includes quadrupole built in to them. However, if for people who already have our own coupling capacitor, we have the quadrupoles for that. To have a good sensitivity, coupling capacitor needs to be related the value to the actual capacitance of the object. So recommended to be more than 0.1 to have a good value of the PD. So for a larger capacitive objects like cable, for example, a larger coupling capacitor would be recommended. So a coupling capacitor must be PD free and should be of low inductance. And also a coupling capacitor is intended for transfer of the high frequency spectrum of the PD signal. Okay, so as we mentioned, the measuring impedance is the main part which converts the input PD current pulses into equivalent output voltage pulses, which then can be measured by the system, the equipment. To reduce the dangerous voltages, the measuring resistor RM is usually shunted by inductor LM. Okay, so the current standard, the IEC 6270 in a latest version 2015 is the horizontal standard, define the testing for objects like all objects, high voltage objects like bushings, cables, GIS switchgear or switchgear, as well as the transformers, seat and instrument transformers, and other type of transformers like power transformer and right type transformers. So it defined the method of measurement, which use a coupling capacitor, direct conventional method, and also defined how the step response, voltage response being applied, and calibration, how the calibration needs to be taken into consideration. It also defines the block diagram of PD measurement. It's similar to what we shown here. There is also a section which defines other non-electrical methods, and also it defines test result evaluation. and it defines recommended frequency band. In IC standard, there is both wide and narrow band. Maximum frequency of 1 megahertz is recommended. So this is the radio frequency of 1 megahertz, where the IC standard define the testing. Keep in mind that 1 megahertz range is an ideal range to cover the whole insulation, because as you increase the frequency range, as you measure at higher frequency, the range of PD pulse travels will be less. That means if you are measuring at 50 megahertz range, the location of PD will be surrounded by nearby area. But if you reduce to less frequency, like 1 megahertz and below, you can cover the whole area. For example, if you connect the connection at the terminal of the transformer termination, if you measure at 1 megahertz, it can cover whole transformer and even the little bit of cable connected to transformer. But if you increase the frequency, you will localize more and more nearby the measurement area. More will be explained later. So with this 1 megahertz, you can cover the whole area of the object under test. But keep in mind that at that 1 megahertz range, also there is more noise will happen. So as you increase the frequency, less noise will be there. But on the other hand, you will cover only localized area. So each one frequency has benefits, and that's why we provide both. Unconventional method. Conventional method, we explained before, involve coupling capacitor and direct connection to the terminals of the object under test. Unconventional method means indirect measurement, which means that methods which we don't connect directly, but we measure the effect and emissions resulted from that PD. For example, electromagnetic PD detection frequency ranges. There are various ranges. High frequency range between 3 megahertz to 30 megahertz, which can be done via, for example, various methods. Very high frequency between 30 to 300 megahertz, and ultra high frequency UHF between 300 megahertz and 3 gigahertz. As I mentioned, as you increase the frequency, the range will be reduced. So for example, a UHF range, the area which we can detect PD will be minimized. That means if you measure at terminations area, only PD near the termination will be detected. This can be useful in area where you want just limit the PD to the termination and surrounding area. And also UHF benefit has a reduced noise measurement. But keep in mind that depends on the medium of the insulation. There might be no PD on UHF range. As I mentioned, depends on the insulation type. For example, when it's talking about liquid insulation in a power transformer, for example, it has a pulse rise time in nanosecond, which equates to 350 megahertz. As pulse travels through transformer to measured area, that will be reduced to around 50 and 40 megahertz range at the measurement area. So there will be almost no PD at UHF range. There will be little, but most of them will be eliminated. So that's why it's used more on GIS. But still, UHF will be useful on transformer. I'll discuss where it will be useful in next few slides. Okay, so for each asset, you need to test in a frequency range according to the testing environment, based on what we want to achieve in PD measurement and what we are testing. We can use various sensors with various frequency range, from high frequency, very high frequency, or ultra high frequency ranges. Coupling devices can be inductive, like for example, Rogowski coil, or we call HFCT. A clamp like this shown here is one example where you can open it and connect around, for example, grounding of the object, and it can measure the PD within the insulation or the object. For example, if you put it on the ground of the transformer or the ground of the GIS, it will be able to measure the PD in that transformer. It has a range of 1 to 100 megahertz range, which is a very good range to detect the PD. There is also various capacitive methods like TEF sensors used in medium voltage panel, for example, and antenna, like various antennas, like UHF antennas, for example. So all of this, whether inductive or capacitive, these sensors don't measure the PD directly, but they measure the radiation in electromagnetic range. And keep in mind that the measurement is in dB, not in picocoulomb, because you are not measuring direct measurement, so only possible in dB, the result. So, and as I mentioned, the PD pulses are attenuated significantly. We are using UHF sensors. And keep in mind that a UHF method cannot be calibrated. So only a sensitivity check is possible, which I'll explain later in this presentation. Let's talk quickly about UHF measuring devices. Basically, UHF signal can be detected in time domain or frequency domain. So a magnitude will be measured, and the frequency spectrum can be measured as well. It is a recommended method as a complementary, basically, measurement. It's a non-conventional method, so it's not as per IC 6270. However, it's a complementary method. So it basically amplifies the broadband frequency spectrum to feed to the detector. So again, both wide and narrow band can be selected in the equipment. So you can select a particular frequency, or you can select the wide frequency range within the measurement. Another non-conventional method where PD is acoustic. Basically, a PD, as we mentioned, it causes various radiations. It causes, one of the radiation it causes are vibration through the surrounding area, and that propagates and travels on, to the surfaces of the outside of the object, which can be detected with the acoustic sensors. So these PD pulses usually happen between 10 to 300 kilohertz, and various methods of acoustic can be measured with piezoelectric transducers or fiber optic acoustic transducer, accelerometers, condenser microphone, sound resonance sensors. All of them, they are methods for measuring acoustic. So keep in mind the attenuation of PD pulses when using acoustic sensor. And one of the primary application of the acoustic is PD location. With acoustic, approximate PD localization is possible, particularly in GIS and power transformer. So it's considered as a later stage. Once PD detected, then acoustic can be as a complementary method to fine-tune and try to find out the location of the PD. There are two types: structure-borne or airborne. Airborne means you just an antenna like the parabolic antenna with a laser pointer detected to outdoor to a specific area like surge arrestor and measure that acoustic signal caused by PD, or structure-borne, where the acoustic travels through the transformer, for example, and propagates through various paths, whether it is reflected or directed, and then it can be sensed on the outdoor structure of the power transformer. Again, acoustic method cannot be calibrated. So this was the introduction of PD testing. Then let us go quickly talk about PD testing on a transformer or power transformer. So as I mentioned, partial discharge breakdown as a small area of overall insulation. Each PD pulses generates different measurable electrical signals. So a local displacement current pulse or current impulse, it goes by a PD, localized PD, and that can be measured at a transformer. Now, using conventional method, I'll talk about three methods. Conventional method using coupling capacitor, using electromagnetic signal or acoustic signal. So here a diagram example of what sensors mounted on a transformer for online monitoring. So as you can see here, for example, there is on each bushing, there is a bushing adapter. Basically, a bushing adapter, we are having bushing adapters for all transformer types connected to the bushing tab. And basically, it's a direct measurement method because it uses bushing capacitance, C1 capacitance of the bushing. It uses that as coupling capacitor. So if your transformer has a bushing tab, then no coupling capacitor needed. It uses basically a bushing capacitance as a coupling capacitor. Just a small box used as measuring impedance, and then coaxial cable connected to the equipment. You can connect at each bushing connection, and can be done in with either 1 megahertz range, which is recommended range for 60 to 70 IEC, or 10 or 20 megahertz range. So it's basically low frequency radio frequency range, and can detect the PD throughout the transformer, and with ability to have measurement at each individual bushing, you will be able to, since you can find the level of bushing, you can find out the approximate location of that PD by comparing these phases, and you can see at which leg or phase that PD can happen. Another type of sensor or UHF sensor can be connected, for example, at the drain valve here down of the power transformer, or we have a UHF sensor can be connected on the flange of the power transformer. And keep in mind that these UHF sensors, as I mentioned, they don't measure PD throughout the transformer, so they can measure PD nearby that area, for example. And the benefit of UHF is that it is less suspected to outdoor noise because the sensor goes inside the transformer and it acts as Faraday cage. So while also measuring at higher frequency, it's less suspected to normal noise of the substation usually happen at low frequency area. But still, for this type of measurement at bushing tabs, we have an adapter called disturbance antenna, which picks up the corona noise, and then it will subtract that from the measurement. This is one of the big benefits we have in our system called gating, which means it can measure the noise and can subtract that and reduce that from the total PD measurement, which give a cleaner result. So within a power transformer, for online measurement, there are basically you will be able to connect at the bushing tabs, and then you can connect UHF antennas down and above. And then you can also connect, in addition to being able to connect on the earth of the transformer using a clamp. Okay, so as I mentioned, origin pulse rise time is range of 1 nanosecond, translate to bandwidth of 350 megahertz, or LC network of the transformer. It will cause attenuation, dispersion, and reflection and filtering of the signal down to below 20 megahertz at the top of the bushing. So measurement at the bushing, they reduce down to 20 megahertz, and that's why this is the range we recommend to measure up to 20 megahertz at the bushing tab. So this signal stays up to some limits in correlation with the real discharge value of QA, calibration according to 60 to 70 IEC. Okay, as I mentioned, electron avalanche causes electromagnetic pulse, which is radiated in all directions from its origin. And discharge in oil or solid material can show frequency component above 300 megahertz sometimes. So in that case, a UHF pulse signal can be decoupled by UHF antenna. Keep in mind that UHF signal cannot be correlated to specific amount of discharge at its origin. So no calibration is possible. So by the way, UHF signal strength strongly depends on the location of the antenna and the travel path of the electromagnetic pulse. So acoustic signal is caused by electron avalanche, again causing a pressure increase, slower transversal and faster longitudinal signal components, signal strength measured with piezo sensors on the transformer tank. Basically, we have active acoustic amplifier, which you can put at the outside of the tank. You can put one or several of them also on the outside of the tank. So usually acoustic signal mostly used for location of the PD when it comes to power transformer in a later stage. So under nitrogen atmosphere, the rise time, as I mentioned, is 1 nanosecond. So keep in mind that the power transformer is highly complex network, so there will be cross coupling. That means a PD happens in one phase, it will reflect to adjacent phase to various degrees. In a shop floor testing or a field or factory acceptance testing, we have a procedure for cross coupling matrix, which again helps to localize PD if you measure at bushings. It's also complex insulation system, the power transformer. It's oil paper, two types of insulation with a press board and porcelain and composite bushing. So all of this will result in a complex insulation system. So I'll give you an example here with a PD source of 3 different measurement. On the picture on the left-hand side here is the electric PD pulse taken from the test tab of the bushing, for example. You can see the PD here signal shown on the left-hand side. On the middle area is an example of a UHF pulse taken using UHF antenna and the oil valve, drain valve sensor. It's a UHF measured as a UHF signal. On the far right-hand side, it's acoustic signal measured from the same PD on the tank wall. Note that usually here you have 3 red, blue, and green graph on the far right represent acoustic for 3 different acoustic sensors. The black one represent a PD pulse used as a trigger. So that means you can measure the acoustic after the PD happens. How do you know PD happened? We are a trigger used by a normal PD. So acoustic alone won't be very extremely useful. It's usually used in combination with a triggered normal PD. So combination of both, then you can find out the approximate location method. So in a transformer, basically typical defects are sharp points and particles within the transformer, localized defects, surface and tracking discharge within layers, various layers like between paper layers, fiber bridges in the oil, for example, floating potential like floating particles, gas insulations like void, like bubble in oil and solid, delamination in paper, for example, and solid. So all of these various imperfection will cause a PD. Keep in mind that PD in a power transformer is localized. That means some of these faults, they can only be detected with PD, no other method. And transformer acceptance testing done in lab or in factory is one of the most important tests done in final factory acceptance test according to various IEC and IEEE standard. So usually typical acceptance level are 250 picocoulomb for power transformer and much less 10 picocoulomb for dry type transformer. So that's why in ideal condition, in the lab or factory, the noise floor should be below 20 picocoulomb, so that with a dry type should be below 2 picocoulomb, so that with the shielding, and separated the ground to be able to measure at this low picocoulomb level accurately with a sensitive equipment like our equipment also usually used to be able to measure accurate measurement. So it can be either this power source can be either single or three-phase induced or applied test, voltage test. It can be either using quadrupole at the test tab, or it can be used via coupling capacitor if there is no test tab. Then a coupling capacitor is needed, like shown in the second picture from left. The PD system suitable can be either with AC, DC, or impulse sources. And then using the acoustic location, we have a software feature, add-on software, which helps to find a location of the PD. This is for a transformer which did not pass the PD acceptance criteria. So usually for large transformer are very expensive. So production and testing schedule are usually tight, and undertaking large transformer is time consuming. So having a location result is as precise as possible, speeds up the process of correcting action. Okay, so basically in acoustic, a textbook triangulation method means having 3 acoustic sensors at 3 different locations, and then using time of flight of the PD, we can triangulate and find the location. However, keep in mind that in a real transformer, interior is not homogeneous. It's a complex network with various objects in which pulse travels at different speeds. So it cannot, and also tank is not a thin membrane, and there are multiple transmission paths. So sound speed in a transformer oil is different than the sound, for example, in different locations. So that's why we use various different methods, like a flat problem, putting in horizontal and vertical. That will give us a better indication of the location of the PD pulse using our software. Okay, so let's move on to the PD testing on GIS. Basically, GIS cross-section shown here is a enclosure, and that enclosure is a grounded potential, and in the middle is high voltage conductor and filled with SF6 insulating gas. And usually a simplified version diagram shows that the electric field shall be homogeneously distributed throughout inside. So an electrical field strength should be below critical field strength. However, if you have an imperfection, even small, within manufacturing, for example, it will cause inhomogeneous field around that imperfection area, which leads to increased PD, and that might cause excessive electric field, and that can be result in a PD eventually. So partial discharge emits as electromagnetic emission in the form of radio waves, for example, light, heat, and also in form of acoustic, and also can probably leads to chemical byproducts. So basically, PD signal indicates an imperfection which can need to be identified and probably localized and classified. Here you can see, for example, depends on the type of PD. Some PDs, they can be also leads to optical effects. They can be lead to a pressure wave detected by sound or acoustic. So it can discharge effect, which can be leads to, for example, dielectric losses and high frequency waves, which can be measured with a conventional method we explained before. Chemical effect might introduce chemical effects, for example. Sometimes it leads to, let's say, excessive hydrogen in transformer, for example, which can be detected with VGA. And then heat. We here discussing in GIS, 2 major types used are UHF and acoustic. So according to the usually PD measurement can be done according to 270. We are in a fact, this is used in a lab or in a factory using a coupling capacitor with a high voltage source with a high sensitivity, which leads to measurement of even down to 5 picocoulomb. So and it can be, but keep in mind that this method cannot be applied in service. Chemical method is a slow process, so barrier insulators separate the gas compartment, therefore limiting the range of detection. That's why a chemical process is not widely used. For example, an optical also cannot detect certain types, like voids, for example, cannot be detected with optical method. That's why we are focusing on, when it comes to GIS, focusing on acoustic and UHF. So in an SF6 gas, it has electronegativity, which leads to a rise time of 100 picosecond, which is much faster than rise time of nitrogen or air. So that's why frequency spectrum show up to several gigahertz, which make it ideal for using UHF measurement. That's why in GIS, UHF is used mostly for GIS measurement. And PD activity emits transient electromagnetic waves, and the GIS enclosure acts as a waveguide, which means that PD cannot go outside the GIS area, because that is the GIS grounding area surrounding the gas. It will act as Faraday cage. So basically the GIS enclosure acts as waveguide, and good thing about UHF, along with the GIS enclosure, the noise will be almost much less and not a big factor. You can only measure PD happening inside the GIS rather than noise from outside. But keep in mind that GIS is a complex signal. It's not as simple as might seem. So you can see that here PD propagates through areas left and right of the GIS, which then can be detected with various sensors shown in black here, left and right. As I mentioned, the GIS is a complex network again, and and that complex geometry leads to a reflection of the signal and attenuation of that signal. And the impedance of the waveguide is basically a function of a logarithmic function of diameter over length. And even the surface roughness influences the signal propagation through dispersion. And these effects are highly frequency dependent. But PD pulse is converted to pulse package like that due to these reflections. So wideband measurement is required to achieve a good sensitivity in entire GIS. And since UHF sensor measure in specific range, as I mentioned, not the whole range, so several sensors is needed to cover the whole GIS. So multiple UHF sensors is needed, and they act like antenna to convert electromagnetic wave to voltage, then shown in as dB on the equipment. There are two types of methods to measure the sensors. Usually GIS manufacturers, they come with built-in sensors. We at Megger are OEM provider for various GIS manufacturers. However, if you have all GIS, which there is no PD, PD sensors, UHF sensors, you can add retrofit to add sensors. For example, we have a sensor called external flange sensor, which used in, for example, spacers between two chambers. Then we have also some very old GIS, they have inspection window. Then we can have the window sensors, for example. But the most sensitivity will be achieved, the best sensitivity will be achieved with built-in PD sensors. Based on the SIGRE standards, there is a sensitivity verification procedure, which is a two-step procedure for acceptance criteria. So that means first step done at factory, a second step done at after installation locally. It described on this SIGRE standard mentioned here. Basically, for the unconventional measurement like this UHF, calibration of apparent charge in picocoulomb is not possible. That's from SIGRE TBA 654, page 4. So the measurement will be in dB microvolt or dBm. Okay, so basically you can see here in a PD propagates through the enclosure and then will picked up by several sensors, here by stronger signal picked up by first sensor, then weaker signal picked up by the next sensor. So by measuring through several sensors, approximate area of the PD can be also realized. So let's talk about sensitivity verification. Step 1 done at factory, basically, which means done in parallel with both conventional 60 to 70 method using coupling capacitor and high voltage source, and unconventional. So basically a real PD source of 5 picocoulomb applied, like a hopping particle or artificial PD within the system is applied, which is known to be 5 picocoulomb, will be measured by a conventional method, and then the level of that 5 picocoulomb, how much will cause in dB microvolt, will be registered with UHF sensors. That means that signal in a dB microvolt caused by 5 picocoulomb PD will be known. And then an impulse generator will injected through one of the sensors, adjusted until same signal happens on the UHF, which causing the 5 picocoulomb, equivalent to 5 picocoulomb. So that means the level of impulse, which equivalent to 5 picocoulomb, is known. That usually provided by factory and done at factory, only valid for that particular GIS design and particular sensor installed in that GIS. And then impulse generator will be provided with the sensor, so that the utility or receiver of the GIS can use the impulse generator with equivalent impulse to inject that impulse to those sensors and measure that resultant in dB microvolt or dBm in other sensors. So as a step 1, it injects that through the UHF sensor and check sensors in surrounding area how they measure. They should be measured in a closed relation to what measured at factory, for example. Okay, so basically each sensor needs to pick up a signal at least once to make sure that all sensors can pick up a good manner, and at least one measurement through each part of the GIS needs to be done. So basically the sensitivity verification confirms that the given measurement setup is capable of detecting PD pulses of 5 picocoulomb and above. This is the purpose of sensitivity check. Okay, so the summary basically of the unconventional method: PD occurs due to the imperfection defects. PD in SF6 emits UHF range and it caused by PD pulse packages picked up by various antennas, and it cannot be in picocoulomb, in dB microvolt, on dBm. So basically the PD can happen in various things, as I mentioned. In summary, it can happen in rotating machine, transformer, bushings, cables, GIS, instrument transformer like CTVT. So it can cover whole life cycle, whether during research and development, shop acceptance testing at factory or field testing, or online monitoring, for example. Okay, I think I'll conclude my presentation at this stage.
So here we conclude the presentation and we are open for the questions and answer session. So I would like the participants to put your questions in the question box, and whoever has asked the questions, so now we have a panelist. We have Matthias and Mr. Mohammed on the panelists. So they'll be answering on the same.
Thank you everybody for listening to the presentation. We have now starting a question and answer session. We have one question which asks, can we reach the bushing test tab on the transformer while the transformer is energized, or this is an offline method? The bushing tab can only be installed while the transformer is offline. So that means you need to take the transformer to offline, install the bushing tab, then you take it online again. In that case, you can monitor and measure at any given time, since you already installed the sensors at the transformer. Okay, we have another question. At HV switching yards, there are lots of TR humming sound, or I think he means transformer humming sound. Will it affect the test for cable termination? Matthias, can you answer this question?
Yeah, of course, I'm glad to comment on that. So when it comes to on-site PD testing, then any noise and interferences that reach our measurement are always an issue, of course. And therefore, our instruments have different techniques to eliminate disturbances, external disturbances from our measurement as good as possible. So it always depends on what instrument you are using, on what asset you are measuring, and what kind of disturbance you are facing. If you approach a situation where you have noise on your measurement, then the first step usually is to try to get rid of the source of the noise, because that is obviously the most efficient way. However, for on-site testing, that often can't be implemented. Then the second step would be to try to avoid that the noise reaches your measurement. And that can be done, for example, by filters that can be, as an example, can be implemented between a high voltage source and the equipment under test, and that will filter out the high frequency parts of the signal and therefore block external interference to your measurement. And then if that is also not applicable, then we are facing a situation where we are recording the noise and then try to get rid of it afterwards. And then we have multiple ways of doing that. One of them would be a frequency selective measurement. So with a lot of our equipment, you have a spectrum functionality so that you can select the frequency range in which you want to measure, and then you can record where you have your noise, where you have the signal that you want to detect, and you can set a measurement frequency accordingly so that you have less interference from external sources. This can also be done with hardware filters in a lot of cases that can be implemented and that are part of our portfolio. And if this frequency selective filtering is not an option, then we can refer to gating. So gating means that we try to measure the disturbance signal and provide it to the gating path of our instrument. That can be done with, for example, these gating antennas with CTs. That also highly depends on the setup that you have. However, if you are capable of measuring the noise at a different location and feed it to our instruments on the gating input, then our instrument is capable of eliminating it from the measurement. So we have various approaches to eliminate noise from our measurement. which is working with great success in a lot of occasions. But yes, of course, the sensitivity for on-site measurements can be limited in some cases. That is unfortunately the case. And then we are back to the topic that Mohammed talked about, where we are talking about different measurement approaches, which are more or less suitable for on-site and offline measurements.
Thank you very much, Matthias. That I think also answers another question which talked about what technique you use for filter out noise, which already Matthias answered in multiple methods. Another question is, do medium voltage and high voltage equipments, PD, use same detectors technique, or are there special detection equipment for HV? I believe they both exactly the same. Only the coupling capacitor is larger or smaller, depends on the voltage rating. If you use the coupling capacitor for offline test, if using CTs for online test, then it's the same. Matthias, you have any additional comments?
Yeah, so the PD itself does not care about the voltage that is applied to an asset. The PD is only correlating to the electric field strength. And if you have a higher voltage applied, then you have a larger insulation dimension, and therefore you still have the same electrical field strength. So the basic principle of measuring PD does not really depend on the voltage level that is applied, but on the field strength, and of course on the insulation material that is being used. And that can, of course, make a difference. I mean, you talked about it, Mohammed. You said the difference between nitrogen and SF6, for example, in switch gears. So if you have a difference in the insulation material, then you want to evaluate if you use a different technique of measurement. But simply because of the voltage that is applied, you don't adjust your measurement technique.
Thank you, Matthias. We have one question: what difference between calibrator Cal2B 200 pico coulomb and Cal2B 500 pico? 200 picosecond and Cal2B 500 picosecond, and when each one is recommended for GIS? Yes, Matthias.
So both of them are functioning well, so you can use both of them. The important aspect to consider is that since the Cal2B 500 has a slightly lower rise time, that means that the upper frequency spectrum is limited. So you are losing some signal strength in the really high frequency range. It is still totally suitable for UHF measurements on GIS, but what needs to be considered is that if you are going for a sensitivity verification, because this device is usually used on GIS for sensitivity verification procedures, then you have to use the same device that was used for the step 1 test in the laboratory. You have to use the same device on site then. If you use a different device for the step 1 and for the step 2 test on site and in the laboratory, then you face the issue that the verification is not really valid. So the important thing is that you use the same device at all times. If that is given, then there's not a huge difference between the applicability of the two. You can use both.
Thank you, Matthias. Another question, is it possible we install PD monitoring system for medium voltage transformer without bushing tab? I will answer this, and if Matthias has comment, he can comment as well. So basically, there are some sensors which requires transformer to be offline, like bushing tab adapter, and also flange UHF sensor, since it is usually on top of the transformer. However, the question is what type of test can be done and what sensor can be installed while it is online. One method is using HFCT, which can be mounted at the grounding of the transformer. However, keep in mind that the ground have usually more noise. However, it can be useful as well. Another thing is, but care should be taken, is connecting UHF drain valve sensor Many customers are reluctant to do it online, but it is possible following extreme care on doing so and knowing dimensions and what would be behind drain wall sensors. So yeah, that's basically possible. Matthias, you have any comments on this?
No, that sounds pretty legit.
Okay, great. We have another question. Can we install additional PD sensors in cable terminations and integrate it with GIS monitoring system? Yes, Matthias, you can comment here.
Yes, that is possible, and we have done that. So we have installations where that is the case. For these installations, we have installed CTs around the grounding sheets of the cable terminations, and then we have installed so-called frequency converter units. And these frequency converter units are taking the HF signal and converting it to the frequency range that our measurement kit, our monitoring instrument requires, and then they can be integrated to a monitoring system. Yes. The same is, of course, possible for portable equipments.
Thank you. Another question is, what is the most effective way and recommended equipment setup to test vintage GIS without built-in sensors?
Unfortunately, the answer is it depends. So we have ways of retrofitting UHF sensors to vintage GIS. There are two different types. You have introduced the EFS, the external flange sensor that can be connected to any unshielded flange. So that means a non-metallic part of the GIS where the signal can actually exit the GIS. The second way would be to implement sensors to the inspection windows of the GIS. This type of retrofitting UHF sensors can be utilized on older GIS if the necessary inspection windows and flange areas are available. For some, that is unfortunately not possible, and then it gets tricky. For a manual on-site measurement, we can do that with an acoustic measurement, but that is kind of limited in some regard. So it is tricky to use acoustic sensors only on GIS because you are fearing that you can pick up a lot of other signals that are not related to PD, and then you have to have an in-depth knowledge to analyze what you are measuring and figure out what kind of signal you are facing and if that is relevant.
Thank you, Matthias. Another question is, frequency band on ICM is 40 kilohertz to 800 kilohertz. How it could be helpful on GIS by changing the range to get rid of some unwanted sources, or know more about signal shard? I'm not sure if I understood the question. Did you understand, Matthias?
Yeah, so the frequency range that is given here is the typical frequency range for measurements according to IEC 60 to 70. If you apply this conventional PD measurement technique, then the big advantage is that you can measure in picocoulomb. Because to measure in picocoulomb, you have to stay below 1 megahertz as per IEC 60 to 70. There are a lot of advantages in going up with the frequency to higher ranges. And that is something that is especially applied on GIS, simply because it shows really good results. For on-site measurements, you usually go up into the UHF frequency range with the technique that you explained. And in this frequency range, the external noise that is airborne, let's say it like that, can't really reach your measurement because the GIS is a metallic enclosure and therefore shielded from external noise. And therefore you have a really high sensitivity when applying the UHF signal because it automatically blocks external sources and signals from the measurement.
We have a question. It says how you can measure noise from different sources, as you told, if you have only one gating input. So I think, Matthias, the question means if there are multiple noise sources while having one gating input.
So first of all, we have instruments with multiple gating inputs. That is definitely an option. So in some rare cases that can be helpful, but usually only for really distributed installations like GIS, where you are measuring somewhere outside in parallel to measuring somewhere inside the GIS hole. So there are instruments with multiple gating inputs. If you are, I mean, we have different ways of picking up noise signals that can be done, as mentioned before, with a CT, that can be done with a disturbance antenna. So depending on what signal you are facing, there can be different methods of measuring it, providing it as a gating signal, or even blocking it by a frequency selective measurement. So it kind of depends on what exact noise you are facing, what is the best approach to eliminate it from your measurement.
Yeah, I agree. Thank you, Matthias. So I think we can conclude our session. If anybody has additional questions, please feel free to send us an email or reach us at Megger. And we have done also webinar, live demo webinar from factory, our colleagues at factory, partial discharge testing on power transformer using coupling capacitor, HFCT, as well as acoustic method to find location of the partial discharge. Very nice webinar. I recommend you check our website or reach us if you would like to view the webinar. Thank you everybody for attending the webinar, and have a nice day.
Thank you and goodbye.